Good evening and welcome everybody. It's Obi-Wan Pez for N Simplex Pachinko. We're going to turn this down a bit here. And going to get into some more math communication that we're doing. Tomorrow we do have a rental inspection, so unfortunately may have to spend a smaller amount of time on tonight in order to make sure that I'm, able to take care of that. So we'll see how things go. Hope everybody's having a good night. And having a good start to your week. Just double checking everything. Cool. Right. So we already talked about mathematical well-being in a previous session. Yes. I think we briefly went over the abstract on this one because it is a paid, access paid journal. Right, we could only go through the abstract anyway, but I'm pretty sure we did. Yes, because the next one is Diamond Open Access. Right. This one was by Kontorovich, and all about the Diamond Open Access experiment, trying to get journals open and access for anybody who wants it. We also looked briefly at X Plays Pokemon and found the Twitch channel. Where is it? Hang on, where is it? Winning Sequence. So if anybody is interested in checking out Winning Sequence, they are playing a currently 4-year mission to see if the number pi, when mapped onto a controller, can then end up beating Pokemon Sapphire. So far, they've made it past the first trainer. Right, so might as well throw that out there. Yep, there we go. Then we have amicable numbers and their connection to the Euler-Totient function, which we did talk briefly about. And then we started looking at the rest of the arXiv that was here and seeing if there was anything that I even had a hope of understanding. And so far, it's been looking like, yeah, not so much. I know I'm slightly down on myself for that, but nonetheless, it's true. Okay. I did receive news from the BOINC, it's the Berkeley. I forget exactly what BOINC stands for, but it is the Berkeley Combined Shared Process application that took the place of, at least on my computer, both folding at home and SETI at home. So I was running some stuff with that, and instead now I'm running BOINC, which on Linux is the Grid Republic desktop. So it allows us to share processing time with whatever projects are interested. So we got, this one is the aliquot sequence. So it goes through and aliquot is the number where you're adding up, or no, you're multiplying all the digits. Exact divisor or factor of a quantity, right. So this is looking at the perfect number question, right? Are there any other perfect numbers? What do we get for aliquots? Do aliquots always terminate? So if you take all of the aliquots of a particular number, add them all together, and then take that number, find all of its aliquots, add them, and then take that number, etc. Will they all eventually terminate? So this is much like our trying to find numbers that are divisible by 3 or 6 or 9. You can repeat the process and see if the digital sum is going to be divisible by 3 and how many times that's possible. Actually, that's not true. Sorry. The digital sum, there we go. If we're dividing by 3, if it is divisible by 3, the digital sum will eventually, if you take its digital sum and then that number's digital sum and that number's digital sum, will be a multiple of 3. So. Also need to give credit where credit is due. Thank you to Exoda and Neone and all of the other people at No Copyright Sounds. Although you can't hear it now if you are live on the stream, we will enjoy No Copyright Sounds because it has no copyright, despite apparently throwing a copyright error. Anyway, the number, what is this? 3,576,396 has an aliquot that is around 10 digits long, or aliquot sum, maybe. I mean, it must be a product, right? Anyway, right, as we continue through taking its aliquots, then the result that we get ends up with a much larger number of digits, starts shrinking down again, comes back up. Almost makes it to 120 digits long before shrinking back down to a known value. So some number that has already been checked before. In this case, it looks like it is about, right, 6, 7 digits long, which makes sense. So 3,576,396 in the aliquot sequence has terminated. Awesome news for anybody running this particular thing. And I don't know if anybody else is working on problems similar. And we also pulled up the Journal of Open Math Problems. Cute. They made it into eyeballs. Okay, that just started. is the editorial. I think Alex Kontorovich, yeah, production editor, said he was on that. Interesting. My goodness. Anyway, since we have this, okay, so we picked I just picked whatever the first available one is. Okay. Right. We were also going over linear geometry to see if we could understand any of the stuff that's in here. This appears to be fairly over my head, but makes sense because this is a new concept. So here the authors are defining all of the terminology and definitions and examples. So we talked about this a little bit. Density of the primes in the eigensurface of symmetric group S3. Again, not really way above my pay grade, but Harnack inequality for nonlinear equations driven by normalized infinity Laplacian. I know what some of those words mean. All right. Yeah, we're already getting well beyond me there. Repair scheme for a distributed storage system based on multivariate polynomials. That seems interesting. I know that there has been a lot of work done, especially since the 1980s, and in fact, before computers were really huge in like the 70s, I want to say, they were working on some concepts of like error correcting codes just for like code, for like cryptography. Goal of a distributed storage system. Sorry, Hiram Lopez, Gretchen Matthews, and Daniel Valvo, the authors. The goal of a distributed storage system is to store data over multiple storage nodes. A linear code, which is a vector space over a finite field, may be used in distributed storage system setting to allow the information stored on a failed node to be recovered using the information stored on the remaining nodes. The general idea is the following. The information to be stored is encoded into code words using a linear code. Every code word is distributed across nodes so that each node stores a symbol. Recovering a failed node exactly is equivalent to fixing an erasure in the code word. A repair scheme is an algorithm that recovers the value at any node using limited information from the values at other nodes. Under certain conditions, some repair schemes require less information than standard approaches to repair. Thus, the mathematical goal is the following. Design a set of vectors in such a way that every entry of every vector can be recovered from the rest of the entries. In these notes, we use evaluation codes, meaning that the set of vectors is a vector space over a finite field, and every vector depends on the evaluation of a certain polynomial. Give an explicit description of an exact repair scheme. In other words, give the algorithm describing how every vector entry can be recovered from the rest of the entries. In these notes, we use the trace function from finite fields to describe the repair scheme. An evaluation node is a linear code defined by evaluating a collection of polynomials on a set of points. Reed-Solomon codes, most well-known family of evaluation codes, are defined by the evaluation of single variable polynomials up to a certain degree on a set of points of the finite field f sub q of size q. The design of linear, exact repair schemes for distributed storage systems using evaluation codes began with the foundational work of Guruswamy and Wouters, in which they developed a repair scheme, GW scheme, to efficiently repair an erasure in a Reed-Solomon code, RS. GW scheme highly depends on the dual of a Reed-Solomon code, which is a generalized Reed-Solomon code. For a general framework of evaluation codes, see Jaramillo. For the dual of an evaluation code, see Lopez et al. 2021. GW scheme inspired the linear exact repair schemes for algebraic geometry codes and Reed-Muller codes, Chen and Zhang 2019. Similarly to Reed-Solomon codes, Reed-Muller codes are defined by evaluating polynomials up to a certain degree in m variables on the points m sub super f super m sub q to the t. In these notes, we develop a repair scheme for several failures on a distributed storage system that is based on Reed-Muller codes, provided the positions satisfy a certain restriction. The approach we develop in these notes, which relies on the dual of an evaluation code, is different from the one used in Chen and Zhang, and gives the basis to extend it to other families of codes, for example, family of Cartesian codes. Let q be a power of a prime and f sub q to the t be a field extension of degree t. Okay, fair enough. So f is a particular field we're using. Okay, q is a power of a prime, p. And then degree t is the degree of the polynomial we're using. Let C be an nk linear code over f sub q to the t, meaning a k-dimensional f sub q to the t subspace of f super n sub q to the t, q to the t. The elements of f sub q to the t are called symbols, and the elements of f sub q are called subsymbols. As f sub q to the t is a vector space of dimension t over f sub q, any code word c belonging to the code word space c, or more generally any element w in that field, the total k-dimensional space, okay, can be represented using n symbols or tn subsymbols. The field trace can be defined by the polynomial trace sub f sub q to the t. So the field extension of degree t divided by the original field f sub q as a function of x is a member of the extension space. Can't tell if that's a function of x or they're doing something else. Given by the following. Okay, trace is going to be equal to, or is going to be of the form x to the q to the t minus 1 plus etc. So all powers of q all the way down from q to the t minus 1 all the way down to 1. So I guess t minus 1, the power, is going to be 0 on q, which makes it x to the first. For the sake of convenience, we'll often refer to the trace simply as trace of x rather than doing the subfield thing when the extension being used is obvious from context. Right, we're pretty much always going to be using that particular trace in here. The following property of the trace function is crucial to developing the repair scheme. Remark 1, let B be a basis, Z1, Z2, all the way through ZT, for the field extension on degree T over the general field. Yeah, I think. Then there exists a dual basis B prime of and over the same such that the trace of Zi Z prime j is equal to delta ij, which is of the form 1 if I is j and 0 otherwise. That is something out of TensorCalc. I recognize that. Yeah, it's a good thing I actually did some work out of this. There. Kronecker symbol, or Kronecker delta. Not quite the same because Kronecker delta has a superscript and a subscript, but you know, it's so close. It's really kind of the same. They're almost the same. In this case, B and B prime are called dual bases for alpha in the field extension. Alpha is going to be equal to the sum of all of the traces alpha zi z prime j. Nope. Z prime I, because I has to be the same as j. Okay. We're defining alpha. Oh, that's not good. Oh no. Raven Violet, good evening and welcome. How's it going? Good, nice. Thus, given dual bases B and B prime, determining alpha is going to be equivalent to finding the trace of alpha zi for all I belonging to t. So any number, any integer 1 through t. Okay. By Reed-Miller codes, we mean the evaluation codes obtained when polynomials in m variables up to a certain total degree d are evaluated at all the points of f super m sub q to the t. Precise definition is as follows. Okay, let the field be the polynomial ring of m variables. Right, so all of our subscripts are different x's, different independent variables x sub m. or x sub I, whatever, over the extended field. Denote by extended field x is going from x sub 1 to x sub m, which are less than d. Less than or equal to, right. So m is allowed to be anything less than or equal to d. The set of those polynomials up to a certain total degree d. Assume P1 through Pn is equal to the field f super m sub q to the t, fixing an order on n of the form q to the tm elements. Reed-Miller code of degree d is going to be given by the following. All right, so there's some sort of function f that uses the field as inputs. And we get f belongs to the extended field using x1 through xm, which then has to be a subset of f super n sub q to the t. Right, okay. So we're allowed to say that we're taking a function of the whole field, and that will similarly take the function of each of the p variables from above. Note that a Reed-Solomon code of dimension k of length q to the t is defined as the following. The dual of a Reed-Miller code denoted by Rm is a set of all alpha, such that alpha times beta is 0 for all beta being the Reed-Miller values that we're getting, where alpha times beta is the ordinary inner product, a dot b, ordinary inner product of f super n sub q to the t. The dual code has been extensively studied in literature. See, for instance, the following Delsart and Huffman and Pless, where it is shown that the dual of an RM code is another RM code. So, Reed-Miller of the field and d dimensions dual is going to be equal to the Reed-Miller of the field d-dimension dual, where d-dual is of the form m times the size of the field subscript q to the t, all minus 1, then minus d, minus 1, is equal to m times the quantity q to the t minus 1 minus parentheses d plus 1 or minus d minus 1. Okay, exact repair scheme. In terms of distributed storage systems, each entry C sub I of code word C in C space, so defined below, C is a linear code. So I'm seeing it as the code word space up top there. Represents the information stored on one of n different storage nodes. Informally, when one of the storage nodes fails, meaning that it is unable to serve a data request, an exact repair scheme is an algorithm designed to recover the information of the erased node in terms of data held by the other storage nodes. Formally, we have the following. Let C be a linear code over the extended field of length n, dimension k, given by a collection of functions, fancy f, and a set of evaluation points a. A linear exact repair scheme for capital C over the extended field consists of over the field f sub q consists of the following. For each alpha star in A and for each alpha in A without alpha star, a set of queries, q sub alpha of alpha star, must be a subset of the extended field. For each alpha star in A, linear reconstruction algorithm that computes, f of alpha star is equal to the sum of lambda I zi for coefficients lambda I in B, and a basis z1, z2, etc. through zt for the field, extended field over field sub q, so that the coefficients lambda I and fq linear combinations of the are f sub q linear combinations of the queries union alpha in A without alpha star trace of gamma f of alpha such that gamma is a member of the query space q sub alpha of alpha star. We often omit the word linear because we only consider linear exact repair schemes in the first place. Repair bandwidth B is the number of subsymbols the scheme downloads to recover the erased entry. As any element C depends on NT subsymbols, the number B over NT can be seen as the fraction of the code word that is needed by the exact repair scheme in order to recover the erased symbol. Okay. Lost something on my disk. It's no worries. It's around. Okay. It is important to note that to recover a symbol C sub I in the extended field space of code word C, these B elements of the original field f sub q rely on entries Cj, where j is not equal to I, of C, but are not necessarily B of them. In order to recover a certain symbol Ci of a code word, these B elements rely on entries C sub j as long as j is not equal to I. So you must have a certain number of other letters in the code word, but there are not necessarily B of them. Oh, we could have extra information. Jeez. You learn by reading once and don't use ChatGPT? Well, probably not. But I found that this is a good way to at least try and like push my boundaries a little bit, because otherwise it, just brain starts atrophying. So if I try to at least think about the stuff that it's saying and how it relates to things that I do know, then I can sort of at least somewhat understand what's going on. Right. So in a one erasure repair scheme, yeah, I mean, you saw what I just realized there, right? What is all of that trying to say? It is important to note to recover a symbol C sub I within the extended field space F sub Q to the T of a code word C, the B elements of the field F sub Q rely on the entry C sub J, which are other terms of the code word that are not the same as C sub I because we're missing C sub I, but there are not necessarily B of them, meaning, yeah, you saw the look on my face because I was like, I just don't understand what you're saying, because you have to have at least, and that was the key, you have to have at least B of them in order to be able to figure out the information, but that was the key. So you know a lot. Nowhere near as much as a lot of the other math streamers, by the way, who have like masters and doctorates in, much more deep areas. I only ended up getting to like, I mean, I still took senior level classes in my bachelor's, but like I took nowhere near as many senior level math classes as like my spouse did, because she was majoring in math, and so when she majored in math, she ended up taking like 12 different courses in like advancing levels of mathematics. I pretty much like, the highest level stuff that I really remember is my junior year, where we did abstract algebra. So abstract algebra, you're basically starting from nothing, and you're saying, okay, what do we have to assume in order to create mathematics? And then from there, how do you build off of that? And then after spending a couple of years in the field trying to teach, I went back and got my master's in applied and computational mathematics at Johns Hopkins, which, like, to give him credit, it's a pretty good degree, but it also, like, I didn't do necessarily the same level of rigor as I think the people who are at Johns Hopkins Homewood campus, the like actual Johns Hopkins University in downtown Baltimore. So I got my master's in applied and computational mathematics in 2010, and then haven't done any actual formal schooling since then. Why am I so humble? I'm at least second generation Boy Scout. And like, I know my limitations. Yeah, I have spent my entire life. Yeah. I've spent my entire life basically around people that I recognize are far more qualified than I am to do a lot of things. I'm very much a generalist, so I will go around and I will grab little bits and pieces of everything that I can understand, that I can reach, and try and understand it to the best of my ability. That is not necessarily going to get me to understand it, but at least I can understand something and then start pushing my boundaries on it to try and see if I can understand it better. That is one of the reasons that I picked up tensor calculus by Pavel Grünfeld, because I'd already taken partial differential equations, and like I was going back through his videos on partial differential equations, and I was like, I need something more. I need I was kind of curious if don't be the smartest person in the room. Know how to get the person you need. Yeah. So, like I said, I'm a big generalist. I not only did I like not super apply myself into getting higher and higher levels of mathematics, I also was like, oh, well, I can't take this class in my sophomore year, so let's drop that and let's add in a class that I've always wanted to take. So I just added in an elective course, which did not count for my major or like anything, which was kinesiology, be an EMT. And I was like, I want to be an EMT. And my advisor's like, you don't have time for this. Like, you need to take other classes. I'm like, look. So I was majoring at the time in mathematics education at the secondary level. So 7 through 12, right? That was my intended career path. And so I went and I took that, and I ended up being an EMT for 4 years. Had like licensed jobs on an ambulance corps for 2, and then I had my national registration for 2 more years after that. We moved to Maryland, and I never pursued it. I was just kind of like, look, I'm good in terms of like, I didn't want to be an EMT for the rest of my life. But it's definitely a worthwhile experience. It was taught me a lot. And not just about like, life saving, but like how the group ended up running their, I hesitate to say business, but how they ran the core to make sure that it sustained itself. Most of which was charitable donations, because they were a nonprofit that was sort of attached to the University of New Hampshire and sort of attached to the Durham, New Hampshire Fire Department. Sort of. So it's been an interesting ride. We're currently now living in the UK, and I don't have a professional job that I go to every day. I do, however, have 2 different positions, one for the Scouts and one for our parents' organization at my kid's school, where I'm the treasurer. So I'm doing a bunch of accounting, which is also a new skill for me. So like I'm learning kind of a lot. And really that's kind of where you want to be. Figure out what skills you want and then get those skills. And then you don't necessarily need to like stick around in the same job forever, especially in this economy. Like my dad had a 401k, it was going great, and then it was completely stolen by Bernie Madoff and all of his jackass companions. So, like, he's got basically nothing to show for his years of corporate work. And it was, that point in my 20s that I was just like, well, fuck it. I'm not gonna put up that. I mean, a lot of people don't have money. And then lots of people have jobs and then still don't have money, partially because they're not paid enough, and partially because they don't spend, well enough, unless, of course, they don't get paid enough in the first place to sustain their living, no matter what level they live at. But a lot of people do live outside their means. So there's kind of a two-pronged issue that's going on there. And it does tend to be a bit of an issue. I mean, people in the US certainly have more money than many different other places in the world, no matter how, like, not wealthy they are in the United States, right? There's still a lot of places in the world that operate off of single dollars a day, and you're fine. So you can't do that in the US, certainly. Anyway. Before I get too much into what's his name, Mike from PA's wheelhouse of talking politics on stream. Right, adapt the GW scheme of one erasure from Reed-Solomon codes and Reed-Muller codes. In Lopez 2022, authors developed a repair scheme of one erasure for certain decreasing monomial Cartesian and augmented Reed-Muller codes. We decided to focus on these notes, Reed-Muller, to determine in Theorem 1 to what degree a Reed-Muller code can be repaired using ideas similar to Goswami and Wouters. Let Reed-Muller, that be a Reed-Muller code such that d is less than or equal to m times q to the t minus 1 minus q to the t minus 1. Q to the t minus 1 minus q to the t minus 1. There exists a repair scheme for one erasure with bandwidth at most b is equal to q to the mt minus 1 plus t minus 1 times q to the m minus 1 times t minus 1. Okay, let C, which is the code word, be of the form. It's a function of all of those p's that we saw up above, which are members of the Reed-Muller function. Assume that the entry of C corresponding to p star, which is lowercase p1 through pm, belonging to the field f super m sub q to the t, meaning f of p star has been erased. Okay. So the data, any of the star data is erased. Whatever that means, right? I mean, is unable to be accessed. Recall that Z1 through ZT is a basis for field extension f sub q to the t over f sub q. For I belonging to t, define the following t polynomials, which we refer to as recovery polynomials r sub I of x. What predisposition do you need to understand this? More than me. So this is probably something in higher level analysis. I took a class in neural networks, which is not the same as this, but I can at least kind of lean a little bit on it to like sort of understand some of the stuff that's there. It's not the same by any means, but it's got some like little bits of rhyming in it. That is trace, yes. TR. Okay, so r sub I of x is going to be the trace polynomial of z sub I times x sub 1 minus p sub 1. P sub 1 is a piece that has been erased. What is P actually? Fixing an order, elements here. Okay, the function on it's not up here. Just kind of like looking at it, make sure. Right, the field on the the function on the field is going to be of the form, right? F of P sub 1 through F of P sub n. So this is telling us that we're taking elements from the field itself, pumping them through this function, and then we're taking like basically a vector of all those things. And that's going to be our function of the field total. Okay. So P1 through Pn are all elements of the field F super M sub Q sub Q to the T. So little P1 through Pm are the things that are missing. All right, so the trace of Z sub I times Z1 minus P1, no, X1 minus P1, all over X1 minus P1 is going to be equal to Z sub I plus Z sub I raised to the Q times X1 minus P1 raised to the Q minus 1 plus all the way down to guess that would be up to Z sub I raised to the Q to the T minus 1. Right, so Q is now being raised to the Q's being raised to the 0th power in the first term. Q is being raised to the first power in the second term. Q is going to be raised to the Q squared in the third term, Q to the third, Q to the fourth, Q to the fifth, etc. All the way up to Z sub I to the Q to the T minus 1 is where it stops. At the same time, same thing is happening to X sub 1 X sub 1 minus P sub 1. We're trying to find the difference between the thing that's missing, P sub 1, and X sub 1, which is polynomial ring of m variables. Well, anyway, it's all divided by X sub 1 minus P sub 1, which then takes out one instance of X sub 1 minus P sub 1. Normally, those would have the exact same numbers, like exact same numbers of them in each individual term. So that also means that Z sub I Q to the 0 which then gets us just z sub I in the first term, should have parentheses x sub 1 minus p sub 1, all raised to the q to the 0 minus 1, but it gets divided by x sub 1 minus p sub 1, and so it gets wiped out. Actually, wait, what? Ugh. Okay, so if we assume that that's true, then... Oh, no, jeez. Yes, right. It doesn't have the minus 1. It's 1 minus 1 because of the 1 at the bottom as well. Right. So we end up getting a 1 minus 1 is 0 for the first term. So x sub 1 minus p sub 1 is raised to the 0th power in the first term. Okay, we're good. All right, so we get that all clear. As d is less than or equal to m times q to the t minus 1 minus q to the t minus 1, then d dual is equal to m times q to the t minus 1 minus d minus 1, which is greater than or equal to m times q to the t minus 1 minus m times q to the t minus 1 minus q to the t minus 1 minus 1. Which is going to be the same as q to the t minus 1 minus 1, which is greater than or equal to the degree of r sub I. Because the degree of r sub I is q to the t minus 1 minus 1. Okay. Follows that every polynomial r sub I of x defines an element in Reed-Muller space dual, meaning that r sub I of the field is going to belong to Reed-Muller of the field dual. As a consequence, we obtain the equations r sub I of p erased times f of p erased is equal to negative summation across the entire field without the erase stuff. Okay, yeah. So all of the things that we do have, sum up their recovery values, r sub I of p, times their function values, f of p, for all i's that we have, as r sub I of the erase stuff is equal to z sub I. Applying the trace function to both sides of the previous equations and employing linearity of the trace function, we obtain the following. It's the summation of the trace of r sub I of p, f of p. Define set gamma, being p1 cross all of these spaces. Then r sub I of p is going to be equal to z sub I if p is within the set, and the trace if it's not within the set. All right, we're going to explore that in a few minutes. So we're going to go on a 3-minute break. Thank you, everybody, for coming. Thanks, Raven Violet, for being here, and we shall return very shortly. Righto. Welcome back. We will get on to bit of fitness, as always. Alright, try to do them as best we can. Got all sorts of stuff all over the floor. It's great. Alright. And 1, 2, 3, 4, 5, 6, 7. Shoot. 15. Come on. Great. Losing form. 25 is good enough. I think that was 25. And if it wasn't, that's close enough. Okay. All right. Trace of z sub I times s sub p minus p1 all over s sub p minus p1, where s sub p is the first entry of the point p belonging to the field. Note that p star is a member of gamma. Therefore, we obtain that we have the trace of z sub I f of p star equals the sum over the field, accepting all of those missing p stars, of the trace of r sub I of p times f of p, which means that it's gamma accepting p star trace r sub I of p f of p plus interesting. Okay. The field accepting gamma of the same. Yes. Okay. Set theory-wise, we're taking the whole field and we're taking out gamma. And then we're taking gamma and taking out p star, which is the same as taking all of f and taking out p star only. Okay, that makes sense. Good. Okay, and then the only thing that's changing for the next one is to look at the trace of r sub I of p times f of p is equal to the trace of r sub I gets substituted as the trace of z sub I times s sub p minus p1 over s sub p minus p1. Okay, which then says that we've got now the trace of, so the first one ends up being the trace of z sub I times s sub p minus 1, and they rewrite that just as the trace of z sub I times s sub p minus p1. And then the next, they reposition, say the trace is linear, so by its properties, the trace of AB is going to be the trace of A times the trace of B. So here we have the trace of f of p over s sub p minus p1. They're just shifting the s sub p minus p1 bit to the denominator of explicitly the second part. Properties of the trace function imply that the entry f of p star can be recovered from its t-independent traces, trace of z sub I f of p star, which can be obtained by downloading the following information from every element p, which is not p star. If p is in gamma accepting p star, download f of p. If p is not in gamma, download trace of f of p over s of p minus p1. Hence the bandwidth is given here, which boils down to q to the mt minus 1 plus t minus 1 times the quantity q to the m minus 1 times t minus 1. Corollary. Let Rm be a Reed-Miller code such that d is less than or equal to q to the t minus q to the t minus 1 minus 1. Then there exists a repair scheme for one erasure with bandwidth at most b equals q to the t minus 1. By definition, 2 rs equals rm, so therefore we obtain the result as a consequence. Okay. 2 erasure repair scheme. I'm going to guess this is harder. All right. So same stuff as before. C is equal to f of S1. It's right. We should read the top part. Keep the same notation as in previous sections and develop a repair scheme that repairs 2 simultaneous erasures, f of S prime and f of S star, on a distributed storage system. Provided erasure positions satisfy the current or certain condition. Let C be the code word, f of S1, etc. through f of S sub n. Reed-Miller code d less than or equal to, same thing there, n equals q to the tm. Assume that C has the 2 erasures as written above, where S prime is equal to S1 prime, S2 prime, etc. to Sn prime, and S star is equal to S1 star through Sn star. If there is j belonging to n, such that S prime sub j minus S star sub j is within the field star, then there exists a repair scheme for the 2 erasures with bandwidth at most given here. Kernel of the trace, alpha, exists in the field such that trace of alpha is 0, has dimension t minus 1 as an f sub q vector space. It's the same basic setup as before. Hey, Famished. How's it going? Ready to define repair polynomials. For I in t, take piece of I of x equal to tau times trace of z sub I times the quantity x sub j minus s sub j star all over x sub j minus s sub j star, and q sub I of x being trace of same but primes instead of stars. Access? Oh. Yep, gotta get done. I'm terribly sorry. All right, following similar proof scheme of theorem 1, we have the following two equations. P sub I times, P sub I of S star times F of S star plus P sub I of S prime times F of S prime is going to be equal to that summation over there. And similarly for Q sub I. Definition of the P sub I's, we have the following. So P sub I of S star is equal to tau z sub I, and P sub I of S prime is equal to tau times trace of z sub I. And similarly for Q sub I's. The equations become the following. So here we have tau times z sub I times F of S star plus tau trace of z sub I times F of S prime. Similarly for this, but they're in reverse positions, and this one, our Q sub I, does not have a coefficient out front. It's just Q sub I of S prime is equal to Z sub I. Done. Okay. The last two equations imply the following. We claim that the elements f of s star and f of s prime can be recovered from the set following here. To prove this claim, we take the following steps. For I in t minus 1, trace can be recovered from set R in equation 6 here. We have tau in the kernel of the trace, whose f sub q basis is the following. Hence, there exist a sub 1 through a sub t minus 1 in f sub q, such that tau is equal to the linear combination of a sub I alpha sub I z sub I from 1 through t minus 1, and the trace of tau times f of s prime is equal to the sum from 1 to t minus 1 of alpha sub I times the trace of z sub I times f of s prime. Therefore, trace tau times f of s prime can be recovered from step 1. So that's going to be the same as it showed up in theorem 1. That's all the same stuff. Some of the particulars might be slightly different, but same idea. From step 2, equations 4, 5, tau z sub I f of s star can be recovered for all I. The element tau times f of s star can be recovered from the traces by the following equation. Dual basis, remark 1, thus f of s star can be recovered by the following equation. From step 3, equations 6 and 7, trace of z sub I times f of s prime can be recovered by the set R. Similarly to step 3, element f of s prime can be recovered from the trace of z sub I times f of s prime. complete the proof. Woo! As a consequence of the claim, both erasures f of s prime and f of s star can be recovered from the set given here. Observe that p sub I is going to be tau z sub I if s is in gamma star, and tau times the trace of this stuff if s is not in gamma star. And then q sub I of s is going to be z sub I when s is in gamma prime, and similarly trace if s is not in gamma prime. Where s sub p is the first entry of the point s in the field m q to the t. Thus, the set R can be rewritten as this mess. Thus, both erasures can be recovered by downloading the following information from every element S. If it's in gamma star, download that. If it's not in gamma star, download the trace of it. If S is in gamma prime, download download f of s. If S is not in gamma prime, then download the trace of that thing. Bandwidth is at most this, which concludes the proof because it is actually the same. L erasures repair scheme. We're not going to do this one. But similarly, right, there's going to be a generalizable formula for this, and it's just going to be able to keep going from there. Summary conclusion, distributed storage system stores across data. Sorry, I should have popped this out like way long ago. I was going to finish up psychology, but figured do boring stuff first. Yeah. I still need to do some training for something. A distributed storage system stores data across multiple nodes with the primary objective of enabling efficient data recovery even in the event of node failures. Main goal of an exact repair scheme is to recover the data from a failed node by accessing and downloading information from the rest of the nodes. In these notes, we extended the exact repair scheme developed in 2017 from Reed-Solomon codes to Reed-Muller codes, with several erasures that satisfy certain conditions. Right on. Largest common subtree of two random trees. Let's see how this goes. Omer Engel, Kalen, Atamanchuk, Anna Brandenberger, Zeta Donderwinkel, and Robin Khanfir. Abstract. We study the size and structure of the largest common subtree between two independent BNIME trees, conditioned to have size n. when the trees are critical with finite second and 2 plus kth moment, respectively, for some, kappa. We prove that the LCS has size of order root n and is approximated by the length of the 3 paths meeting at a central node. Moreover, we show that the largest common subtree between 2 critical independent BOINC trees with size n and finite second moments may be much larger than root n, implying that our result is tight. We also pose a number of open questions and suggestions for future research. Any Carbot fans in the house? This game is tight. For trees, T, T prime, and T double prime, say that T double prime is a common subtree of T and T prime if T double prime is isomorphic to a subtree of both T and T prime. Makes sense. Size of the largest common subtrees of T and T prime is denoted by LCS TT prime. The purpose of this paper is to study the LCS when T and T prime are 2 independent random trees. Natural setting is that of BOINC trees conditioned to have size n. The following theorem is a less detailed version of our main result. Theorem 1.1. Let tau sub n and tau sub n prime be independent critical BOINC trees conditioned to have size n whose offspring distributions have a finite 2 plus kappa for some kappa greater than 0 and finite second moment respectively. Then there is a finite random variable x greater than 0 for which n to the negative 1/2 times LCS tau sub n tau sub m prime approaches x as n approaches infinity. On D. Is there a D anywhere in the paper above this? Nope. Didn't mention it. We remark that we view trees just as graphs with no additional structure, such as vertex labels or plane embedding, even though in our proofs we use the Ulam formalism for trees wherein vertices have a natural order. In Theorem 1.3, we show that this result is tight, in the sense that having finite second moments for both offspring distributions is not sufficient. Our main result is Theorem 1.2, which relates the limit x to the scaling limits of the BOINC trees. To state that result, we need some additional definitions. Let mu be equal to mu of k, where k is greater than or equal to 0, and mu prime be equal to mu prime of k, where k is greater than or equal to 0, be 2 critical and non-trivial offspring distributions, meaning that 1 is equal to the sum as k goes from, as k is greater than or equal to 0 for all k's. K times mu of k must be equal to the sum of all k mu prime of k, where k is greater than or equal to 0, and mu of 0 and mu prime of 0 are greater than 0. A Pen might know them. Probably not. Moreover, we assume that mu and mu prime have finite second moments. Sigma squared is of the form sum all k's greater than or equal to 0, k minus 1 squared times mu of k is less than infinity. And sigma prime squared is of the form, again, same deal. So that must also be less than infinity using mu prime instead of mu. Let us denote by tau and tau prime two independent BNI matrices with respective offspring distributions mu and mu prime. Formal definition of BNI matrices is given in section 2. We will hereafter only consider n for which p number tau equals n greater than 0. And p of number tau prime equals n greater than 0. All right, Anakin. Good luck out there. Get the applying. Woo! We view tau sub n and tau sub n prime as compact metric spaces equipped with their graph distances. For any metric space E equaling E, D, and lambda greater than 0, we write lambda times E equals E, a vector, E, lambda d for the metric space obtained by rescaling the distances on E by lambda. Fair. It's well known, citation needed, citation there, that 1 over root n times tau sub n, 1 over root n times tau sub n prime is going to start approaching 2 over sigma times fancy tau, 2 over sigma prime times fancy tau. With respect to the Gromov-Hausdorff topology, where tau and fancy tau prime are two independent Brownian continuum random trees, more precisely, if E equals E sub s, where s is 0 or 1, is anywhere between 0 and 1, is a standard Brownian excursion, then fancy tau and fancy tau prime have the same law as the quotient metric space of interval 0 to 1 induced by pseudodistance d sub e, defined as follows. S1 and S2 are between 0 and 1. S1 is smaller than S2. D sub e of S1 and S2 is equal to E sub S1 plus E sub S2 minus 2 times the minimum of E with regard to S1 and S2. Finally, we introduce our limit quantity. For any two compact metric spaces, E equaling ED and E prime equaling E prime D prime, set phi of EE prime equal to the supremum of the following. 1/2 times d of x1, x2 plus 1/2 d of x2, x3 plus 1/2 d of x3, x1, such that x1, x2, x3 are in E and x1 prime, x2 prime, x3 prime are in E prime, such that d of x sub I, x sub j equals d prime of x sub I prime, x sub j prime for all possible i's and j's within those bounds. Right, they are between 1 and 3 inclusive. Okay. When E and E prime are compact real trees, then phi of EE prime responds to the maximum total length of a common Y-shaped subtree and of E and E prime. For details on compact real trees, the Brownian continuum random tree, and the Gromov-Hausdorff topology, we direct the reader to citation 27, also 5.1 for brief summary. Now let tau star and tau star prime be two independent rooted trees whose laws are characterized by the following. For all integers k greater than or equal to 0, the root of tau star has k children with probability k plus 1 times mu of k plus 1. And the root of tau star prime has k children with the probability k plus 1 times mu prime of k plus 1. conditionally given offspring size and root of tau star, respectively in tau star prime, the subtrees of tau star, respective of tau star prime, of these children are independent binomial trees with offspring distribution mu it's not respective, is it? Ugh. Mu prime. We refer to these random-rooted trees, tau star and tau star prime, as root-biased binomial trees with offspring distributions mu and mu prime, respectively. For rooted trees T prime and T double prime, we say that T double prime is a common rooted subtree of T and T prime if there are graph isomorphisms from T double prime to both T and T prime that map the root to the root. Write LCS dot TT prime for the maximum size of a common rooted subtree of TT prime, and we're now ready to state our main result in full form. Whoa. Brain falling out yet, anybody? All right, theorem 1.2. Assume that 1, 1, and 1, 2 hold. Keep the above notation and set C sub mu mu prime equal to E of LCS dot tau star prime. If there exists kappa greater than 0 such that the sum of k to the 2 plus kappa times mu of k is less than infinity, then the following convergence and distribution on R holds jointly with 1 over root n LCS tau sub n star. Approaches as n goes to infinity. C sub mu mu prime times phi of 2 over sigma times fancy tau, 2 over sigma star sigma prime times fancy tau prime. Figure 1. Two real trees with their largest common Y-shaped subtree highlighted in red. Veragazi, good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We're talking about some subtrees that belong to binary tree distributions. We're coming to some level of understanding. It is not entirely obvious what I am attempting to learn here, but you know what? It's still alright, because it's kind of fun to go through it and see what I understand and what I don't, and try and figure stuff out from there. If anyone does have any particular questions, also feel free and ask. I am a 15-year journeyman, I suppose, teacher of mathematics, between the levels of, roughly speaking, basic algebra and differential equations. So that was a sophomore year math majors class, as well as many other people who could have taken it. I know, who's it? Computer science, engineering, a bunch of other people usually had to take multivariate calculus, differential equations, and linear algebra, or some combination of those three. Depending on degree program. Right, our proofs, in fact, give, under the assumptions of Theorem 1-2, that for any c greater than 0, 1 over root n LCS tau sub n, tau sub floor Cn prime, as n goes to infinity, is going to get us c sub mu mu prime phi of 2 over sigma times fancy tau 2 times root c over sigma prime times fancy tau prime. But to ease notation, we will not prove this more general theorem. Mercifully. Just to remind everybody, we do have a wonderful budding math community here on Twitch. These are our awesome other math streamers. So we have Slim from the Academy of Useless Ideas, Dr. Gold from Actual Education, Dawn Factorial, E.N. Stuckey, Zach from E to the 2i Pi, Merriweather Remark, Penn Center, Phobostream, Physics and Depression, Talos Teaches, and the Tutor Wizard. We also have friends who do study streams, so typically they are trying to learn something in particular and want to bring you along with them. So we have Rendeo, Math Spellbook, Fizzbuzz, Sunaao, and Walking Stick Library. All a bunch of fun people, so if you head on over to their channels and give them a follow as well, any of them can usually help out with anything you might be interested in. Again, if I'm online, which usually is Monday and Wednesday for mathy type stuff, and gamey type stuff on Tuesdays and Fridays, I'm always willing to do some math. So, let me know if you have any particular questions. Otherwise, I will continue on my usual schedule. So our Mondays are math communications night. So we do some like paper reading or going over some math news that might be out there. I know a couple weeks ago we talked about Alex Kontorovich, who is a content creator, but also a math professor at Rutgers, I think, who is currently working on trying to create an open open math journal. So we talked about this, and we also have it. I might have closed it. Yeah, I probably closed it. The Diamond Open Access is to make sure that literally nobody is paying for either access to the articles or ability to publish. So that is one of the issues with a lot of modern math journals, in fact, any science journals at all, is that they are currently owned by a hedge fund manager. Yep. And usually it's just the same one. And so you have to pay that person in order to get access to the journal, and you also have to pay that person if you want to publish in that journal. A number of people have been calling for open access math journals, wherein in some cases you do not have to pay anything to be the reader, but sometimes you do have to pay a fee in order to publish. The Diamond open access model, Alex wrote here, is that nobody pays for it. He just goes online and like sets up a space for it, and other members of the editorial board just like spend a couple hours a week reading journal articles and determining what could be good for next month. So the only stuff that's actually like that they need to pay for is like one staff member who does have to do this as their job, to like organize and then get everything into place, and the web hosting, which I think they said like over the course of the entire year, the entire, any one journal is going to cost somewhere on the order of $3,000. And so basically they just go out there and get funding. So from their institutions or from a donor or from fundraising. And that one person that they have hired as like their, manager to get the layout and stuff like that, I believe that they said that they're also managing other journals in the same group. So they end up getting, at least a decent small salary for what they're doing. But everybody else is pretty much volunteer. It was my idea that if I go back to the United States and become a department chair, that I would allow or push for any of the people in my department, if they want to go and be a referee for any of these things, and it'll count for couple hours a week or something like that of like building community in the math, or building community within institutional whatever. Building inter-institutional community. There you go. So it's interesting. It's an interesting idea. We'll see how that shapes up. I want to come back to it in like a year or something and see what it's like. We will go back to the Journal of Open Math Problems. I think it's the Journal of Open Math Problems is the journal that Alex was doing there, which is called Jump, and is just going to be like a repository for these are open math problems. Can anyone figure them out? And here are the solutions to these interesting problems if anybody does figure them out. Okay, discussions. Concrete examples of cases where Theorem 1-2 applies. Family of size-conditioned critical Bian-Aime trees with finite variance offspring distributions contain several unusual combinatorial families of random trees. In fact, one does not need to even look past offspring distributions with finite exponential moments to find many well-studied models. Here are some. If we set mu of d equal to 1 minus mu of 0 equals 1 over d for some d greater than or equal to 2, then tau sub n is distributed as a uniform d-ary tree on n vertices, assuming that n equals md plus 1 for some integer m greater than or equal to 0. If we set mu of k equal to 2 to the negative k plus 1 for all k greater than or equal to 0, then tau sub n is distributed as a uniform rooted plane tree on n vertices. If we set mu of k equal to e to the negative 1 over k factorial for all k greater than or equal to 0, then after randomly labeling vertices, tau sub n is distributed as a uniform labeled tree on n vertices. 1, 2 applies to any pair of trees from the above list, ignoring labels and plain order when looking for common subtrees. One may wonder if the condition that one of the two offspring distributions has to have a finite 2 plus kappath moment is necessary, or just a consequence of techniques. The following result shows that 1.2 is false if we allowed kappa to be 0, implying that our theorem is tight on this generality. Theorem 1.3, for any gamma less than 1/2, there exists a critical and non-trivial offspring distribution, mu, satisfying the sum of k squared mu of k for all k's greater than or equal to 0, less than infinity, such that for mu prime equals mu with high probability, LCS tau sub n prime greater than or equal to root log to the gamma of n as n approaches infinity. We prove this theorem in section A. Outline and proof overview. We present some standard structural results for BNI trees that we use throughout the paper, as well as a few key lemmas about heavy-tailed random walks. We consider the largest common rooted subtree for two independent unconditioned BNI trees with finite variance offspring distributions tau and tau prime. In short, we prove that the size of the largest common rooted subtree with two subtrees, which we denote by LCS dot tau tau prime, is well approximated by h times t of ht of tau and ht of tau prime, the minimum of their respective heights. Height function ht. Okay. Specifically, we show that p of height tau and height tau prime is less than or equal to h, where h raised to the negative epsilon times LCS dot tau tau prime must be greater than height of tau and height of tau prime plus 1. Decays super polynomially in H for any fixed epsilon greater than 0. Let us explain how knowing that LCS, Jesus, 45 pages. I didn't look at that before. Is useful for dealing with reasonably large degrees. Suppose that U is in tau and U prime is in tau prime, two vertices that correspond to the same vertex in the largest common rooted subtree. Let U1 through UK, K, and U1 prime through UK prime be the children of U and U prime in tau and tau prime respectively. Then there are at least K and K prime factorial ways to pair children to try and build large common subtrees, a union bound that we cannot afford when trees are not bounded. However, if we know that LCS dot behaves as the minimum of the heights, then we know that LCS dot of tau of U, tau prime of U prime must be either less than or approximately equal. Or like, it's not significantly less than, because that would be 2 going like that. The sums of all heights of tau and the sums of all heights of tau prime. Temporarily let tau and tau prime denote the subtree rooted at dot in tau and tau prime respectively. Leaves us with a sum we can control instead of gigantic union bound. From here on, the presence of large degrees makes the argument more technically complex, so for simplicity of the exposition, we will focus on the remainder of the proof outline on the case where mu equals mu prime equals 1/2 delta 0 plus 1/2 delta 2, so that tau sub n and tau sub n prime are binary. We now sketch how we prove that 1.5 decays quickly. We control the probability through bootstrapping. If b sub epsilon is the event in 1.5, we bound p of b sub epsilon in terms of p of b sub epsilon minus nu for some small nu, improving the exponent in the bound each time this is applied. More precisely, let T dot be a largest common rooted subtree of tau and tau prime. Let P be a path in T dot, starting from subtrees starting from the root that walks up the tree at each step, proceeding into whichever of the two child subtrees is larger. There are essentially two options for how the bad event B sub epsilon can occur. For all V belonging to P, the subtree of T dot rooted at V that branches off from P has size bounded above by h raised to the epsilon minus nu times the height of tau and height of tau prime plus 1 for some fixed nu greater than 0, but the sum of the sizes is nevertheless bigger than h to the epsilon times same height expression. There is some vertex v in P, so that the subtree rooted at V, which branches off from P, has size bigger than h to the epsilon minus nu times height expression. In the first case, we can use the known tail bounds for the sizes of BOINC matrices, proposition 2.5, along with big jumps principle for random walks 2.8, to show that 1 has exponentially small probability. By the construction of P, if 2 occurs, then both subtrees stemming from V in T dot are larger than h to the epsilon minus nu times the height expression. By independence of disjoint subtrees in BOINC matrices, then we approximately obtain two independent copies of the bad event B sub epsilon minus nu, allowing a divide and conquer strategy using the previous iteration of the bootstrapping. This allows us to improve the upper bound on 1.5, and recursively applying the argument then gives an arbitrarily good polynomial bound. One key consequence of having good bounds for 1.5 is that P of LCS dot of tau prime is greater than h, will be less than or approximate to h raised to the negative second power. All right, I think we're going to stop here. Having some, good times. Let's see. We are going to go, I think, jump in with Dr. Danny Anduza over at Paleontologizing, who is talking about the Phytodinosauria that may, in theory, be allowed to be genetically sequenced, brought back, question mark. Well, that's interesting. So we'll see what happens there. I hope you all will come back tomorrow for more blueprints. We are on day, like 11 or something like that. and trying to figure out the mystery. I'm sure we've got a long time still left to go. And then we have on Wednesday our next math stream, which is going to be on Calculus 2 material, which we've been working on cracking the GRE from Princeton Review. So we'll see you next time. Hopefully you come on back in, and if you have any questions, let me know. We'll talk about mathy type stuff. My name's Obi-Wan Pez. This is N Simplex Pachinko. Catch you next time.